All right, a matrix is a rectangular arrangement, also called an array of numbers. And this matrix has rows and columns. So if we look at our matrix over here on the left side, we look at our matrix over here on the right side, rather. We got matrix A. We normally name matrices with capital letters. And then this right here would be the rows. The rows would be over here on the left-hand side. And the columns would be up here at the top side. It is kind of important that we can be able to count the number of rows and count the number of columns. So we would say this matrix is matrix A, and the dimensions of this matrix would be the rows by the columns. So this would be a 2x3 matrix. There are 2 rows and 3 columns. We can also identify the elements in that matrix. And some books and videos will identify that element as maybe like A1 comma 2, but that's kind of confusing with this notation, because this notation is just saying, hey, this is matrix A, and it's a 2x3 matrix. This notation is saying, hey, this is matrix A, but we're talking about the element in the first row and the second column. So I don't necessarily like this notation, but it's okay. I prefer the lowercase a, and then the 1 and the 2. Lowercase a is an element in capital A in position 1, 2. 1 being the row, 2 being the column. So what position or what element is in row 1, column 2? Row 1, column 2 would be -2. Row 1, column 2 would be -2. What about maybe like row 2, column 1? 2 would be there. Good. So we can identify elements as well using either notation. This notation and this notation are very similar. One uses a comma, but they do mean 2 different things, even though they look very, very similar. We can talk about matrices being equal. 2 matrices are equal if they have the exact same dimensions. So the dimensions have to be equal in order for these matrices to be considered equal as well. Also, the corresponding elements have to be equal, meaning that very first element in the very first row, very first column, has to equal that very first row, that very first column. Every single element in that exact same spot has to be equal all the way through the board. So if we look at that idea and we say, hey, I'm telling you that these 2 matrices are equal, then what element or what number has to go right there where that t is? 2. So t has to equal 2. T has to equal 2. They're equal. They have the same dimensions. These are both 2x2 matrices. What about this h right here? What element would have to go in that position? What number would have to go there? It would be 3. This is just lining up those corresponding elements, corresponding positions. What about m? Good. And what about a? Good. We're just lining those up. They are equal. And if they're equal, those corresponding positions have to be equal also. And we can use that to solve a whole bunch of equations. Number 2, we have a 2x1. This is actually a 2x1. We have 2 rows and 1 column. We have 2 rows and 1 column. So we can say that these are equal because they have the same dimensions, and there's a big equal sign in the middle. But if they are equal, what can we say about 5x and y? They have to be equal. We don't know what x and y are yet, but I do know that 5x and y have to be the exact same thing. And then what about 5x plus 4y has to equal 10? How might I go about solving this for x and y? This is called a system of equations, and it's really like, I don't really need you to know how to do this the way we're going to do it today, but I need you to understand what a system of equations actually is, because we're actually going to use matrices to solve these systems after spring break. So this is really just to review, what is a system of equations? In Algebra 1, you learned 2 ways to solve systems of equations. This is also a really good review if you plan on taking the SAT, because I guarantee you, you're going to see a system of equations problem on the SAT. How do you solve systems of equations? There's two ways. You can use substitution or elimination. In this case, since y is already by itself, it would be a pretty good idea to use substitution. And this y, I'm going to substitute that y right there. I'm going to change that y to 5x, because y is equal to 5x. So we get 5x plus 4. We're going to change this y right here. We know what y equals. It equals 5x. So there's the substitution, and that's equal to 10. 4 times 5x is 20x. 5x plus 20x is 25x. And 25x equals 10. 25x equals 10. And then we can divide both sides by 25. And we can simplify that. Divide both by 5. 10 divided by 5 is 2. And 25 divided by 5 is 5. So if you plan on taking the SAT, you're going to need to know how to solve systems of equations. And then we can plug in 2 over 5 back right here for x, because we know y is by itself. So y equals 5 times 2 over 5. The 5's actually canceled out, and we get y equals 2. We get y equals 2. Take some time and see if you can figure out what x, y, and z are equal to in number 3. I'll give you maybe a minute and a half, because it really shouldn't take you much longer than that. They're not super complicated equations like we just solved. They're actually much easier. But see if you can figure out what x, y, and z are equal to in number 3. I'll give you a second to do that.
What did you say, x was equal to, or not x, y?
Y was equal to 2 in number 2. Yeah, let me write another y right here. Y equals 5 times 2 over 5. The 5's canceling out. So y equals 2. Try number 3. If 2 matrices are equal, the corresponding elements must be equal also. The corresponding elements must also be equal. All right, number 3. What does x squared have to equal? 25.
Oh, sorry.
How might we get rid of the squared? We might take the square root, which is perfectly correct. The square and the square root cancel out. So I bet almost all of you wrote x equals 5, right? But I would argue there's another number I can plug in for x and get positive 25 also. Negative 5. So anytime we take the square root to solve an equation, we do need to include the positive and the negative. Because negative 5 squared also works, right? Negative 5 squared also works. Y equals 9. Y equals 9, because 9 and y are corresponding elements. There's nothing to solve for there. 12 and 2z are corresponding elements. So we get 2z equals 12. And we can divide both sides by 2. And we get z equals 6. 6. All right, we can also add and subtract matrices. But in order to add and subtract matrices, they have to have the same dimensions. If they do not have the same dimensions, we cannot add or subtract them together. And what are we going to add? We're just going to take the corresponding elements. So that element in the first row, first column, we're going to add it or subtract it to that element in the first row, in the first column of the second matrix. And where's that going to go? That's going to go in the exact same place, the first row and the first column. So we're literally just going to take every single element and add it to its corresponding element in the exact same place. And that answer is going to go in the exact same location of that matrix. So what would that look like in number 4? I'm going to write all of the work out for number 4. I don't expect you to write this down every single time. But what are we looking at? We're looking at this first row, first column, first row, first column. We're gonna add those together, and that is going to go in the first row, first column. We're looking at the first row, second column. We're gonna add those together, and that's going to go in the first row, first column. And likewise, we're gonna do the second row, first column, and the second row, second column, third row, first column, and third row, second column. I would not expect you to write all that out. Maybe just add them together. So 2 plus -6 is -4. -1 plus 9 is 8. 3 plus 7 is 10. 7 plus -11 is -4. 14 plus -8 is 6. And 9 plus 17 is 26. So I would literally just add them together. I would not write all that down. You can, it's not wrong to write that down. But if we're just adding them together, I would just add them together, probably. You can use a calculator to add them together if you need to. All right, what about subtracting? Let's don't think matrices just yet. Let's think this other problem. What if I gave you something like 5 minus -2? What would you probably do for that problem? You'd probably change it to plus, but you're gonna change the -2 to +2 as well. So I would encourage you to do that for matrices as well. We're gonna change the minus sign in the middle to plus. But then what sign do we have to change after that? Literally every single element in that matrix that comes after the minus sign, we have to change every single element. If it's negative, we're gonna make it positive. If it's positive, we're gonna make it negative. And now we can treat this just like the addition problem that we just did in number 4. And I'm not gonna write out all of the steps, like, hey, this plus this. I'm just gonna go ahead and add them together. -7 plus -3 is -10. X plus -x squared is just x minus x squared. It's just an algebraic expression. I can't combine those things, so I just leave it like that. And then -7 and -4 is -11. And then we go and do the next row, 24 plus 76 is 100. 9 plus -3 is 6. 5 plus -x is just 5 minus x. And then we go and do the third row. 2 plus -18 is -16. 4 plus -9 is -5. And 0 plus 7 is 7. We literally just add those things together. It was subtraction. We don't like to subtract typically. It's much easier to add. So change that minus sign to addition and change all of those signs in that second matrix. All right, number 6, looking at number 6. We have 3, -5, which is a 1 by 2 matrix. We have 1 row and 2 columns. The second matrix, we have 2 rows and 1 column. Can we add those together? No, we cannot add those together. So on your test or your quiz next week, it's currently not multiple choice. If you just write not possible, I might give you half credit for that problem. But it's gonna say in the directions, if it's not possible, explain why it's not possible. So why would this not be possible? This is not possible, since the dimensions are not equal. We can't add or subtract matrices, if the dimensions are not equal. On your quiz next week, if it is not multiple choice, that's what you need to write. Or that's the choice you need to pick. Because maybe it's multiple choice, but it still has the explanation in the choices. All right, cool. We can also multiply matrices. We can take a matrix and multiply it by a matrix. But for today, we're not gonna do that. We're gonna look at that tomorrow, when we multiply a matrix times a matrix. But today, we're gonna talk about multiplying a matrix times a number called a constant. That's a constant. We call it a scalar. Why do we call it a scalar? I'll kind of explain that in a little bit. But this is called a scalar. This -3 outside is going to be our scalar. And we're multiplying that by this matrix. And how might we multiply that? You can think about this kind of like the distributive property. We're going to multiply every single element in that matrix by -3. Call it the distributive property, if you will. Draw arrows if you want to. You know how we draw arrows for the distributive property. Draw arrows if you want. We're literally going to multiply every single element times -3. And whatever we get is going to go in the exact same place. If it's in the first row, first column, it's gonna stay in the first row, first column. So -3 times 2 is -6. -3 times -16 is positive 48. -3 times 1 is -3. -3 times -9 is 27. -3 times 5 is -15. -3 times 0 is 0. -3 times 4 is -12. -3 times 22 is -66. -3 times -7 is positive 21. And why do they call this a scalar? We're gonna look at it in a little bit, but if you wanna make something like, maybe you have a shape, or something, and you wanna make it bigger or smaller, and that shape has multiple dimensions or multiple points, we can multiply it by a scalar, and now that shape's gonna be the same shape, but it's gonna be bigger, or that same shape's going to be smaller. We'll talk about that a little bit more in just a second. Number 8. Oh, actually, what is in A32? Which is A32. I like to write it that way. It means the same thing though. We're using commas, not an X. So in the third row, second column. So 1, 2, 3. Third row would be the bottom row, and the second column would be in the middle. That would be -66. Third row, second column. Number 8. We can multiply by fractions. Your calculator can multiply all these for you. So 2/3 times 2/5. 2 times 2 is 4, and 3 times 5 is 15. Cannot be simplified. This is really -9/1 if we're trying to do this without a calculator. 2 times -9 is -18. 3 times 1 is 3. So we get -18/3, which is -6. This is really 8/1. We multiply the 2 and the 8 together, we get 16. We multiply the 3 and the 1, we get 3. And 16/3 cannot be simplified. We multiply the 2 and the 1 together, we get 2. We multiply the 3 and the 4 together, we get 12. And it's gonna be negative, and we can simplify 2/12, divide both of those by 2, and we get -1/6. If you can't multiply it, you can use a calculator. For now, though, we're not gonna use matrix capable calculators. What do you mean by that? Where you can literally type in number 8 exactly like it looks with the matrix typed in as well, and it would do all of the calculations for you with the matrix. We're not using that yet. We will, but not yet. And the element for B in position 12 or 1, 2, that's the first row, second column. First row, second column is -6. Now, can we kind of combine everything we've learned so far today? This number 9 and 10 here really just combines everything we've learned so far. Scalar multiplication, addition, and equality all show up here. So if we're going to solve for x and 20 are in corresponding positions. But does that mean x equals 20? No, because we got a scalar outside, which is a 4. So what do I need to do with that x? What do I need to multiply it by? 4. So I'm not going to do the whole matrix. I'm just going to do the elements that I need. So I'm going to multiply the 4 times the x, and then that 4 times the x has to equal 20. The 4 times the x has to equal 20. And then we can divide by 4 on both sides. And 20 divided by 4 is 5. Cool. All right, what about y? We got y minus 1 and 8 in corresponding positions. That does not mean y minus 1 equals 8, because we got this scalar out front. So we need to distribute this 4 to the y and the -1. So we get 4y minus 4 equals 8. So we distributed the 4 to the y minus 1. Multiplied it by both of those. So 4y minus 4 equals 8. We can add 4 to both sides. So we get 4y equals 12. And then divide by 4 on both sides. And we get y equals 3. All right, so now that we know x and y, there's actually 2 ways we can find z. But I'm going to use this one right here. I'm going to use the 3 and the 6z. They're in the same spot. I'm going to use those. We got to multiply the 4 times the 3 first, though. So we get 12 equals 6z. And we can divide by 6 on both sides. So 2 is equal to z. 2 is equal to Z. All right, number 10, see if you can find X and Y in number 10. I'll give you about, maybe like 2 minutes to see if you can do number 10. And then we'll talk about a brief application of matrices addition and matrices scalar multiplication today. See if you can find X and Y. There is no Z on this one, just X and Y. Just X and Y. And you can multiply all of the matrices by 2. You can multiply all of these by 3 and then add all of them together if you want. That's a lot of work just to find X and Z X and Y in my opinion. But you absolutely could do that. You get a 2 by 2 matrix equal to a 2 by 2 matrix, and then you just have to look at the elements. But then you're literally multiplying every single thing by 2, every single element by 3, adding all of those together. Or we can just look at the X and the Y part, and just look at the X and the Y part. That's what I'm going to do. All right, for X, 2 and 12, but we got the scalar multiple. So 2X plus 3 times 2 is 6. So 2X plus 6 has to equal 12. Subtract 6 from both sides. We get 2X equals 6. And then divide by 2. We get X equals 3. X equals 3 for number 10. And then Y, the 1 and the 7 are all in corresponding positions. Y, 1, and 7. So we're going to multiply the 2 and the Y together. We're going to multiply the 3 and the 1 together and add that. And then that has to equal 7. Subtract 3 from both sides. And we get 2Y equals 4. And divide by 2 on both sides. And we get Y equals 2. Y equals 2. But make sure you multiply by the scalar. Make sure you add or subtract if you're adding or subtracting. And then set that equal to what's in that last matrix in that specific position. All right, so just one quick application of matrices. What we did today, we learned the scalar multiple and the adding and subtracting matrices. So we can actually take ordered pairs and we can actually represent ordered pairs in a matrix. So X, Y would be represented by the matrix X on top, Y on bottom. So if we had this triangle, this is a triangle, it's got points A, B, and C. So this would be A, this would be C, and this would be A, B, and C. Those would be the points. We can actually plug those points into a matrix. And then we can do something with that matrix to maybe change the shape or move this triangle around. And maybe you remember doing this in geometry. Y'all had to do rigid transformations. You took a shape and you had to move it to the right 2, or you had to move it up 4, or both, or you had to reflect it over the x-axis, or you had to reflect it over the y-axis, or you had to dilate it. Maybe you had to make it bigger or smaller. What's another word for dilation? Scaling. So that's why we call it a scalar, because if you multiply by that number, you're making it either bigger or smaller at that point. So ABC would be the points across the top, and then the rows would represent the x values and the y values. It is not a bad idea to label your matrices, especially when we start talking about these real life situations in a couple days. It's going to be really nice that you labeled your matrix. And now what do we want to do? We want to take this matrix and we want to dilate it by a factor of 2. We want to make this triangle twice as big. You guys remember doing that geometry? Maybe you got really confused. I'm not sure. But how can we make this triangle twice as big? We can take all of the coordinates in this matrix 3, 2, negative 2, 1, 1, negative 4. And we can multiply all of these by the scalar multiple of 2. And that's going to give me the new coordinates for my much bigger triangle. That would give me the new coordinates for our much bigger triangle, twice as big, actually, because we're dilating it by a factor of 2. A, B, and C would still be in the same place. X and Y would still be in the same place, but this is going to be that bigger triangle. If you had time, you could actually plot this first triangle and then plot the second triangle and see how it compares to the first. It's actually definitely going to get bigger. 2 times 3 is 6. 2 times negative 2 is negative 4. 2 times 1 is 2. 2 times 2 is 4. 2 times 1 is 2. And 2 times negative 4 is negative 8. So maybe in geometry, they asked you, hey, what are the new coordinates of your triangle? Well, there they are. The coordinates for A would be 6, 4. The coordinates for B would be negative 4, 2. And the coordinates for C would be 2, negative 8. And we would have a triangle that's twice as big as the triangle we started with. We can always use we can also use matrices to represent a translation in geometry. Translation, we're not going to make that shape bigger or smaller because we're not dilating it, but we want to take that shape and maybe move it over and then move it up and down maybe. So in this case, we got a quadrilateral with 4 vertices. The points of the quadrilateral are labeled Q, U, A, and D. We're going to put the X values on top and the Y values on bottom. Negative 2, negative 3, negative 1, 2, 3, 4, and 1, negative 2. That's our quadrilateral in a matrix. Okay, we have a quadrilateral, 4-sided shape in a matrix. What do we want to do with that 4-sided shape? We want to move it 3 units to the right. If I'm going to move something to the right that has X and Y coordinates, moving it to the right, is that going to change the X coordinate or the Y coordinate? That's going to change the X. And in order to move it to the right, what do we need to do to the X coordinate? We need to add 3 to the X coordinate. And why'd you put that on there 4 times? Because in order to add matrices, what has to be true about the dimensions? They have to be equal. So each one of those X values, we're going to add 3. And what about the Y values? We want to move this down 1. So how might we move this shape down 1 space? Kind of like subtract 1, but we're adding. So we're going to add a negative 1. You might be interested in computer programming. Computer programming uses lots of arrays, lots of matrices, believe it or not. Very similar to this, right? Very similar to this. So if you're interested in computer programming, you probably need to know a little bit about matrices, perhaps. Negative 2 plus 3 is 1. Negative 1 plus 3 is 2. 3 plus 3 is 6. And 1 plus 3 is 4. So that's the X values for our coordinate. And then the Y values, negative 3 and negative 1 is negative 4. 2 and negative 1 is 1. 4 and negative 1 is 3. Negative 2 and negative 1 is negative 3. These are the new points for Q, U, A, and D. The X is still on top, the Y is still on bottom. So what is the coordinates of the new quadrilateral for vertex A? It would be 6, 3 would be the new coordinates for that particular vertex.